Hi everyone. I'm so sorry I'm not there today. Actually, it makes me kind of sad because this lesson is one of my ultimate favorite ones to teach, and I love to do it in person, but it's okay. We can do it this way. This is the long-awaited chain rule, right? I know you've heard about it. Well, here it is. Right. So, why even talk about this? Well, here we go. In the last chapter, we learned how to take a derivative of a function like sine x. We learned how to take a derivative of a function like x squared minus 4. But what if the x squared minus 4 was inserted into the sine x? What if we made, like f of g of x type of a situation, and we got something like this, sine of x squared minus 4, right? Well, we don't know yet how to take a derivative of something like this. But today is the day. The answer to all our problems is the chain rule. And it is widely used all over the place. Okay, so what exactly is the chain rule? Well, here it is. Without, throwing too many symbols at you, the chain rule is the following. So suppose you have a function that is a composite function, f of g of x. F of g of x like this. Remember we went over, how to find f of g of x in chapter 1. Well, right now, suppose you have a function like that, f of g of x. Well, remember how in order to create that, we had some outer function and then we had some inner function. Well, what we do is we take a derivative of that outer function, then we go inside and we take a derivative of that inner function and we multiply them by each other. This is one form of the notation that you'll see in places. Another form of the notation was devised by Leibniz. You guys know about Leibniz. This is the one who invented calculus alongside Newton, and then they had sort of like the publishing wars. Anyway, he wrote the same thing but using different notation. So he said, suppose y is f of u, right? Again, it's like f of another function. Then the derivative of this y is dy du, so the derivative of the entire function times the derivative of the inside. It's literally the same thing. They said it in different ways. Okay. Enough of that. Let's actually get in there and do one. Okay? So here it says use the given substitution and the chain rule to find dy dx. Okay, so let's go ahead and start. All right, so the function here is y equals cosine x squared minus 1. So we have cosine, and then inside the cosine, we've got x squared minus 1. So what Leibniz said is, he said, okay, let's call that inside function u. Then we take a derivative of the original function, we take a derivative of that inside function, and then we multiply them. So let's go ahead and do that. So here, y prime is going to be, all right, when we first start reading this function, what is it? It's a cosine, right? And I know the derivative of cosine is negative sine. So the derivative of this is going to be negative sine, except this isn't cosine x. This is cosine x squared minus 1, right? That's the property of this. So I say negative sine x squared minus 1, because that's what my function is. If it was cosine of table, the derivative would be negative sine of table. Okay, times, now we're going to multiply it by the derivative of that u. That came from the inside. Well, what's the derivative of that? 2x. Okay, and then I write it in more compact form, bringing the 2x further to the front. This is negative 2x sine x squared minus 1, keeping the parentheses there. And guess what? Congratulations, you can give yourselves a hand because you have just taken your first derivative using the chain rule. Okay, so now let's do it again. Take a look at sine of root x, and let's kind of, use the terminology of this realm. You have sine of root x. Sine, if you think about it, that's the outer function. And then there is this inner term, root x. We've separated the inner term and we've called it u equals root x. Okay. So here's a little trick of the trade. What we're going to do is we're going to take the root x and we're going to write it as x to the power of 1/2, because we can do that, right? In algebra, that's what we do. Okay, so now let's start taking derivatives here. Y prime is going to be, okay, the derivative of the outer function sine is cosine of what? Root x. Times, now I need to take a derivative of that u, the inside function. Well, I wrote that as x to the power of 1/2. So let's take a derivative of that. So d dx of x to the power of 1/2, what is that? The 1/2 comes down. So now it's x to the power of 1/2 minus 1. Okay? Remember, you always do the same thing. Exponent comes down, subtract a 1. This will be 1/2. X to the power of 1/2 minus 1 is -1/2. Okay, so let's write that here. 1/2 x to the -1/2. And then you're like, wait a minute, am I done? Well, not quite, because we can't ever have a negative exponent. So we're going to rewrite this as cosine root x times 1/2 x to the positive 1/2, right? Anything with a negative exponent comes down. So that's one way of writing it. Another way of writing it, you can say y equals cosine root x all over 2x to the 1/2. Okay. Yet another way of writing it, I'll just put it there, is you can say cosine root x over 2, what's x to the 1/2? Root x. So any of these purple ones are okay, but not the green one with a negative exponent. Okay. Let's do this next one. An object moves along the x-axis so that its position at any time t is given by this. Find the velocity of the object as a function of t. Right, so we did this on the test. We did this in the last chapter. Let's find velocity when we're given position. V of t is equal to the derivative of position x prime of t. Okay, this is equal to, so now we have to take a derivative of this. So look at what you have here. You've got an outer function, which is cosine, and then an inner function, which is that t squared plus 1. So we start with the outer function. The derivative of cosine is negative sine of what? T squared plus 1. Times. Now I need to take the derivative of that inside function, t squared plus 1. That's just 2t. So finally, v of t is equal to negative, bring the 2t forward, sine t squared plus 1. That's all. All right. So we're already using this, terminology, but let's just redefine it one more time. To take a derivative using the chain rule, you differentiate the outside function, and then you multiply by the derivative of the inside function. Okay? So outer functions derivative times the inner function's derivative. Okay? All right, so let's take a look at this one. The first thing you have to do, right? You look at this problem and you're like, okay, cosine 3x. How do you even know to use the chain rule? Because the default, right? The default function for the cosine would just have been cosine of x. Now you don't have cosine of x. You have cosine of something else, 3x. That's what tells you to use the chain rule. And notice this is not a product rule because it's not cosine times 3x, it's cosine of 3x. So once you've established that you need to use the chain rule, the next thing you have to do is determine the outer and the inner functions. So here, cosine is the outer function and 3x is the inner function. So when I do y prime, I start with the outer function, which is cosine. Derivative of cosine, negative sine of what? 3x. Times. Now I zoom in, I go inside and I take a derivative of the inside function, 3x. The derivative of that is just 3. Clean it up. This is negative 3 sine 3x. Okay. This red 3 here is a coefficient. It's outside of the 3x. So you cannot multiply it with the 3x that's inside the sign. Okay? All right, let's do another one. Here, sine is the outer function. X squared plus x, inner. So y prime. Derivative of sine is cosine of x squared plus x, right? I have sine x squared plus x. The derivative is cosine x squared plus x. Times the derivative of the inside is 2x plus 1. And since I have more than one term, I put parentheses around it. Again, that red term is outside of the cosine. So this problem is that red term times the cosine. Convention is we always write the algebraic terms before the trig terms, you know, sophisticated math students and all. So we're going to bring that forward in parentheses times the cosine x squared plus x. Okay, this is so exciting. All right. So as exciting as all these were, you know, you always think to yourself, okay, you know, like it's so much fun to do the chain rule once in a problem. What if you have to do it more than one time in the same problem? So let's do that now. Okay, what if we have to use the chain rule repeatedly? Well, here we go. If you have a function that's got an inner function and that inner function has yet another inner function, then you have to keep doing the chain rule and it literally becomes a chain, hence the name, right? It's like a play within a play for those of you in the play. So in this case, I've got d dx of tangent 5 minus sine 2t. Right. So what I'm going to do is rather than calling it, you know, inner and outer, I'm going to number them so that the outermost function is number 1 and then going inward, it'll be 2, 3, 4, and so on. Okay, so the outermost function here is the tangent. We'll call that the first function. Inside the tangent, I've got 5 minus sine 2t. That's the second function. And then inside the sine, I've got yet a third 2t. So that's what I'm going to do here. It's going to be in, you know, 3 steps. So this is going to be, right, the derivative of this is going to be, the derivative of tangent is secant squared of all of that mess times the derivative of the inside. So what's inside? Derivative of 5 is 0. Derivative of negative sine is negative cosine 2t. then times the derivative of the 2t is 2. So finally, this is going to be, this negative and this 2 will move forward. Negative 2 secant squared 5 minus sine 2t times cosine 2t. Okay, there we have it. Wasn't that super fun? Okay, let's do another one. So what if you have exponent, right? Power rules. Again, we're just gonna work a little bit more with exponents. Right. So you have example 4, number A, y equals the square root of tangent 5x. So very quickly, we learn that it's best to get in the habit of rewriting this. I'm not doing any calculus yet, just using algebra to rewrite the square root as an exponent to the power of half. So this is going to be tangent 5x to the power of 1/2. So now when I want to take a derivative y prime, the first thing I'm going to do is handle the 1/2, right? Because if I look at that function here, right? Suppose I zoom out. What is it that I see? I just see something to the power of 1/2. That's the outermost thing. So that's what I'm going to deal with first. That half is going to come down. So it's going to be 1/2 of this mess to the power of 1/2 minus 1, right? You always subtract 1 from the exponent. That will be -1/2. Okay. Times, so I did the 1/2. Let's cross that out. Times, let's go inside. I've got a tangent. The derivative of tangent is secant squared, 5x, times inside the tangent, I've got a 5x, the derivative of which is 5. So now let's rewrite this over. This is going to be y prime is equal to, we've got a negative exponent here, which is no good. So it's going to be 1 over, 2 is already there, tangent 5x to the power of 1/2 times secant squared 5x times 5. But you know what? I can condense that even further, right? Because 1 times this times that, I could just condense all of them into one fraction. So in the numerator, I've got 5 secant squared 5x over 2. What's to the power of 1/2? It's a root tangent 5x. Okay? So convention is to, sort of condense that way. Okay, let's go on to the next one, right? I have parenthesis to the power of 2. We can just go ahead and get started with the calculus here. The 2 is the first thing that comes down, right? And I'm going to cross that out because I'm going to take care of it. 2, 1 plus cosine 2x. And what's the exponent going to be? 2 minus 1 is 1 times derivative of the inside, 0 plus derivative of cosine 2x, negative sine 2x, times, okay, now I'm done with that, derivative of yet the innermost function, 2x, derivative of that is 2. Clean it up. I have a 2, I have a 2, there is a negative, bring everything forward, -4, 1 plus cosine 2x, sine 2x. Okay. Moving forward. What have we got here? I've got x cubed times another function. So first, this is a product rule. And then I have to implement a chain rule. So let's do it. Okay, u, v. So u is x cubed. V, 2x minus 5 to the power of 4. Fabulous. U prime, small potatoes. This is what we were doing last chapter. 3x squared. Okay. V prime, 4 comes down. 2x minus 5 cubed times the derivative of the inside is 2. Okay. Clean that up a little bit. Combine the 4 and the 2. That's 8, 2x minus 5 cubed. So now, y prime, remember that was uv prime plus u prime v. Okay, so let's do that. Y prime is, right, so this way, x cubed times 8 times this, that's like 8x cubed 2x minus 5 cubed. Plus, this way, I got 3x squared 2x minus 5 to the 4. Okay, but we're not done yet. Because now what we're going to do is see if we can factor anything out, which we can. From here, I can factor out between the x cubed and the x squared. I can factor out an x squared. Also, look, I've got 2x minus 5 to the 3, 2x minus 5 to the 4. I can factor out 2x minus 5 to the 3. So when I factor it out, let's see what I got left. From this term, I took out an x squared, so I have the 8 left. I took out an x squared from the x cubed, so I've got 1x left. I took out 2x minus 5 cubed, so all that went away. Plus, from here, what am I factoring out? The 3 stays. X squared gets factored out. And then from the 2x minus 5 to the 4, I take out 2x minus 5 cubed. So I've got 1 2x minus 5 left. Okay, so y prime is x squared, 2x minus 5 cubed. Let's simplify this. 8x plus 6x minus 15. X squared, 2x minus 5 cubed, 14x minus 15. And that finally is the answer. Okay. So before I move on, I'm going to explain that to you in a different way. Let's bring that here and let's just copy it down here. Okay, don't freak out on me, guys. Okay, so take a look. Back in the day, when you had to factor something like this, if it was, let's say, a squared x cubed plus ax to the 5th, right? What can you factor out of this? You can factor out an a and an x cubed. And then how do you figure out what remains? You kind of do this instinctively, right? But what you're really doing in the background, what your brain is doing is, whatever you factored out, you're dividing each term by that. So now, a squared over a is just a, x cubed over x cubed goes away, plus a over a goes away, x to the 5 over x cubed is x squared. That's what you're doing every time. So let's see if we can apply that here. We said that we were going to factor out from these two an x squared. Let me write that on the bottom. We're factoring out an x squared. And then since these are similar terms, I factor out the stuff that's smaller, that has a smaller exponent. So how do I know what I have left? Well, each time I'm going to divide by whatever I factored out. Okay, so what do I have in the first term? I have an 8. These go away, so I have an x. The 2x minus 5s go away, plus x squares go away, so I have a 3. And 3 of these go away with 1, 2x minus 5. So do you see how I get to the same point, right? Do you have to show me that work, dividing each term? No, of course not. You could always, do it this way, or if you do need to write it down for yourself, you can do it that way. Okay, so hopefully you didn't freak out too much at that. All right, let's move on. Oh my, it's our favorite phrase. Find the slope of the line tangent to the curve, blah, blah, blah. So what do we need? A point and a slope. So first, let's find slope. Slope is the derivative. So what I have here is y sine to the 5x. Remember, that's the same as sine x to the 5, right? That's what sine to the 5 means. So how do I take a derivative? First, take care of the 5. 5 comes down, sine x to the 4, times, go inside, the derivative of the sine is cosine. But I want this at pi over 3. So y prime, let me actually do it here, y prime at pi over 3 is 5 sine of pi over 3 to the 4 cosine pi over 3. 5 sine of pi over 3, root 3 over 2. Cosine pi over 3, 1/2. Oops, this has an exponent of 4. Okay. This is 5. Okay, so what the heck is root 3 over 2 to the 4? Well, okay. Favorite thing math teachers say is when in doubt, write it out. Root 3 over 2 to the 4 is this. So, how much is this? Root 3 times root 3, 3 over 4. Root 3 times root 3, that's another 3 over 4, 9 over 16. So here, this is 9 over 16 times a half. All right, that's going to be 45 over 32. What is this? Slope. Okay, I have a slope. Now I need a point. How am I going to find the point? Well, it's y. Oh, no, I don't need that. I just need the slope. There it is. That's the slope. Okay, I don't need the equation of the time, I don't need the equation of the line. Okay, so take a look at this one. This is a very, college level calculus-y problem, right? This is a sophisticated problem now. Show that the slope of every line tangent to the curve, blah, 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 is positive. Okay, I didn't get anything from that. So let's go slowly through the problem. Show that the slope, y prime, of every line, blah, 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 is positive. Okay, I want to show that the y prime for that is positive. Okay, I don't know what that means, but I know what y prime means. Let me just take a derivative of the y prime. Okay? All right, so let's see what y is. Okay. Let's rewrite this as 1 minus 2x to the negative 3, because it's easier to take a derivative. Y prime is, bring this down, subtract 1, times the derivative of the inside is 0 minus 2, so that's just negative 2. So y prime is multiplying the coefficients, negative 3 times negative 2, positive 6, times this. Okay, I can't have negative exponents. I got to move it down. 6 is okay to stay. That other one moves down. Okay, so I found the derivative. Okay, let's go back to the question. What was it asking? Show that the derivative is positive. Okay, let's take a look at this. Is this term always positive? Well, let's see. The numerator is 6. Okay, that's always positive. So numerator is 6 and always positive. Okay, the denominator has an exponent of 4. Well, what does that mean? Whenever you have something and you raise it to the power of 4, it's always going to be positive. Okay. Positive numerator over positive denominator is always positive. So this derivative is always going to be positive. Okay, thank you very much, everybody. So your homework is on the lesson plan. I know it seems like it's overwhelming to do the homework. Look at each problem. Find a problem like that in the notes. And then start taking the derivative step by step. Okay? All right. We can go over homework questions next week, but you have to come to class with your homework done. Okay. Have a fabulous weekend, everyone. I will see you on Tuesday.